Hello chemists, this is Ms. Placino and you are watching lesson 5.4 on classifying reactions. On today's lesson we're going to look at chemical equations and try to determine what type of chemical reaction is taking place. So, goals for today's lesson. We're going to classify reactions based on the equation. We're going to learn 5 different reaction types. And we're going to be able to use the activity series to predict when a single replacement reaction will occur. I would argue that this top one, classifying reactions, is the bigger takeaway from today's lesson. Let's get started. So, first type of reaction we're going to talk about is a synthesis reaction. And the general format of a synthesis reaction is like this, where we end up with multiple reactants reacting to form a single product. That's just our definition. 2 substances react to form a single product. Key thing here is that the reactants do not need to be elements. That's a really common misconception from new chemists. A and X can be small molecules themselves and combine to make a larger molecule, or they could be elements, they could be one of each. The key is multiple reactants, single product. So here's a good example of that. We have sodium metal, Na, reacting with chlorine gas. Chlorine is one of our 7 diatomics, to produce sodium chloride, NaCl. We know this is a synthesis reaction because we see multiple reactants and one product. If we needed to get this balanced, if I put a 2 in front of sodium chloride, that'll balance the chlorines. I would need 2 in front of sodium. Now those are balanced as well. Okay, the opposite of a synthesis reaction is a decomposition. In that case, we have a single product, a single reactant, in this case AX, decomposing or breaking down into multiple products. So our decomposition reactions are usually pretty easy to identify as there's just one reactant. And again, A and X don't have to be elements, they can just be smaller compounds. We can look at this decomposition reaction. We have ammonium dichromate. So ammonium dichromate would be NH4 in parentheses, 2Cr2O7. You can heat that up and it will decompose into multiple products. I'll have chromium 3 oxide. Sorry about that. Cr2O3. Nitrogen gas, diatomic, and water vapor, H2O. If we needed to get this balanced, how would we do it? It actually isn't quite as bad as it looks. If we put a 4 in front of the water, that'll balance up to give us 8 hydrogens on both sides and a total of 7 oxygens. The chromium's already balanced. Decomposition, 1 reactant, multiple products. All right, up next we have the single replacement reaction. And in a single replacement reaction, we have a compound reacting with an element to create a new compound and a new element. When a single replacement reaction occurs, the element doing the replacing has to replace the element that it is most similar to. In other words, if we're looking at let's say an ionic compound, we know that the metal would come first, and then the nonmetal would be listed second. If B is also a metal, it has no choice but to replace the other metal in the reaction. I wouldn't replace the nonmetal and have 2 metals bonded together. That is not how this reaction will work. Here's kind of like a classic single replacement reaction. We've got magnesium reacting with a solution of hydrogen chloride, also known as hydrochloric acid. We're going to make dissolved magnesium chloride and hydrogen gas. In this case, hydrogen's kind of behaving as the metal, if you will, in hydrogen chloride. So magnesium will come through and replace hydrogen so that it can bond with chlorine, and it will release hydrogen gas. Those are those bubbles that you can kind of see forming around that metal. To get that balanced, you just need to put a coefficient of 2 in front of HCl. But it's that same format as we have above. We've got our compound and our element reacting to form a new compound and a new element. There's a little bit more to single replacement reactions that I'd like to discuss. So if I take sodium solid and I react it with a solution of iron 2 chloride, and I take kind of like the opposite reaction, iron reacting with sodium chloride, only one of those reactions actually takes place. The other, the metal, would just sit in the solution and there'd be no perceivable change. In order to predict which of these reactions would occur, we need to use the activity series. Activity series is table J in your reference table. The way table J works is the most active metals are up towards the top of the table, and as you make your way down, the metals become less and less active. Don't be surprised to see hydrogen on there. Hydrogen tends to behave a little bit more like a metal when it comes to like single replacement reactions. That's why it showed up on this table. We don't use the right-hand side of the table quite as frequently. We've got our most active to least active nonmetals. So the more active metal, the one that is higher up on the table, is capable of replacing a lower metal. The opposite does not hold true. A lower metal on the table, so a less active metal, cannot replace something higher than it. So if we think back to the reaction that we were running with sodium and iron 2 chloride, and iron and sodium chloride, what I would do to determine which one occurs is find the two elements on the chart. Okay, I've got sodium and iron. So it looks like the reaction where sodium is doing the replacing can occur. Sodium is more active than iron, so it can replace iron. But the opposite will not occur spontaneously. Iron cannot replace sodium as it is less active. So just to go back for a second, this reaction, we would write an R for no reaction. Iron cannot replace sodium. I can complete this reaction. I would form NaCl, aqueous, and iron. If I wanted to get that balanced, 2 chlorines, I would need 2 chlorines over on the sodium chloride side, coefficient of 2 in front of sodium on the reactant side, and I'm balanced. So just something to keep in mind with single replacement reactions, you need to consult table J to make sure they will occur. Double replacement reactions. So in a double replacement reaction, you've got compounds on both sides of the equation. More often than not, for our purposes, we're going to see ionic compounds in all 4 of these locations. Basically, what happens in a double replacement reaction is the metal is going to switch places to form 2 new compounds. So A and B will kind of just switch, and we'll create AY and BX. A lot of our precipitation reactions are double replacement reactions. So I've got lead 2 nitrate, that would be PbNO3 2, plus potassium iodide. That's going to create lead 2 iodide and potassium nitrate, KNO3. So we can see effectively there's a little bit more to it than just the metal switching places. And in the next lesson, we'll focus on this reaction in more detail. But the potassium and lead effectively switch places, so I end up forming potassium nitrate and lead iodide. To get this balanced, put a 2 in front of the potassium nitrate on the product side, a 2 in front of the potassium iodide on the reactant side, and that should do the trick. The last one we'll talk about is a combustion reaction, a big crowd pleaser of new chemists. In a combustion reaction, we always create the same 2 products again and again. We're always going to be generating water and carbon dioxide. Another key that we're looking at a combustion reaction is what's on the reactant side of the equation. We've got compounds that only contain the elements carbon and hydrogen. We call those hydrocarbons. The X and the Y are just supposed to represent that these 2 elements can be in a variety of different ratios. We're going to react it with oxygen. So our combustion reactions, that's kind of just a fancy way of saying burning or fire creation reactions. They're going to be very quick, more often than not, and they're going to involve oxygen. These release a ton of energy in the form of heat and light. So if we look at your Bunsen burner reaction, we've got methane gas, reaction with oxygen to create carbon dioxide gas and water vapor. And this is what we'd see. There's methane, oxygen, CO2, and 2H2O. So it's kind of nice with the combustion reactions. You always end up with those same two products, just sometimes not in the same ratio. All right, you know what? Let's go look at some practice problems. All right, so I'm back over in the practice problems where we did balancing in lesson 5.3. And you might have wondered what this bunch of lines are for at the end of the equation. Well, we're going to use that to classify reaction types. And I'm going to go ahead and let's get ambitious. Let's do like the first 10. Why not? These are pretty fast. Okay, so whether they're balanced or not, you can still classify the reaction that's taking place. If we look at question 1, I see multiple reactants and a single product. There's only one reaction that fits that description. This is a synthesis reaction, and feel free to use letters to abbreviate. Take a look at number 2. I've got a compound and an element reacting to form another compound and another element. Yeah, that's single replacement. That's really all you do. You kind of just look at the equation and you start to look for clues like how many reactants or how many products that can give you insight into whether it is decomposition or synthesis. You can look for compounds and elements versus compounds only as your reactants and products. That's a good way to distinguish between single and double replacement reactions. And finally, if you're producing water and carbon dioxide and you've got oxygen as a reactant, there's a really good chance that's a combustion. So pause the video, try out 3 through 10, and we'll check them when you're ready. All right, let's see how you did. 2 compounds on both sides of the equation. Number 3 is a double replacement reaction. I got a single reactant, multiple products. I would argue this is best classified as decomposition, given what we know. Multiple reactants, single products, synthesis. We've got compound on the reactant side, compound on the products, double replacement. I've got like a hydrocarbon and oxygen making carbon dioxide and water. Combustion reaction. Go. Element and compound reacting to form compound and elements. That's a single replacement. Elements combining to make a single product. That is synthesis. Coming down the home stretch, last one. I've got K2O and H2O, 2 compounds combining to make, one product. So even though those are compounds and not elements, we'd still classify that as a synthesis reaction. And that's it. It's pretty straightforward to go through and try to classify the reaction type. Balancing is much more difficult. You'll notice that like the lines stop after reaction 33. Some of the reactions that we look at are not going to nicely fit into one of those 5 reaction types. So it's not that I forgot to put them there. It's just there's a little bit more going on than that, than just simple synthesis, decomposition, single, double replacement, and combustion. I think that wraps it up for today. All right, thank you for tuning in, and I hope you found this helpful.